Potential due a continuous charge distribution. Before, in the last videos, we talked about the potential created by a point charge. Now I want to study the potential created by a continuous object with dimensions. Here we have a continuous object. Okay, we have to follow the same procedure as in the case of electric field. In order to calculate the total field created at the point P, we have to take a small dq from the object. In the case of a line distribution, we have dq equals to lambda dl. In the case of surface distribution, dq equals to sigma dA. And also in the case of volume distribution, dq equals to rho times dv. This is the general case. Let me explain these cases with some examples. Here I take the first example. We have a road. As you see here, we have a road along x-axis with length L. Okay, you know, as before, I want to calculate the total potential created at the point P. At the point P, which is located at a distance d from the road. In order to calculate the potential, as before, I have to take a small portion from here. This one is dq with a length equals to dx because it's along dx. Second, I have to precise the position of this dx with respect to O equals to x. Okay, you know, dq equals to lambda dx. And okay, let me write. Okay. We have, first of all, dq equals lambda times dx. And dq will create at the point P dv. So dv equals to k dq divided by the distance between dq and P. Let's say we have r. So we have here r. Now I want to calculate v. In this case, v equals to integral of dv. So v equals to integral to dv, and we do integral here also. Anyway, now we have v equals to integral dv equals to k dq divided by r, and v equals to k is constant, so we can write k integral dq equals to lambda times dx divided by the distance. R is variable because each time we move dx along the road, R will change. So R equals to d square plus x square. Let's say half. Okay, here we have only one variable because d is constant, lambda is constant, and we have only x as variable. Okay, so this one equals to k lambda, and you know x, if we move dq along x-axis, x will be between 0 and L. Okay, between this point to this point. If we move dx along the road, as you see here, from this point x equals to 0 to this point x equals to L. So we put the limit between 0 and L. 0 and L. And here we have dx divided by d square plus x square. Anyway, I give you the value of this integral. You don't need to calculate this value. I give you as hint. Let's write. So I give you the value of this integral, this one, equals to this one. Okay, I give you the value directly. So we can write here equals to k lambda. We put first of all L in the place of x. We get ln L plus L square plus D square half minus we put 0 minus ln. If we have here 0 and 0, we have finally d square radical. Okay, we have d square power half. Okay, you know d square power half, it means d square radical d square equals to d. So we can write here d. Okay, we can write here ln d. Ln d. Okay, you know ln a minus ln b equals to ln a over b. So we can write v equals to k lambda ln L plus L square plus D square half divided by D. This is the answer of the V created by this road at this point. Okay, look here, I explain. You take dx, x is a position from O to dq, and so on. Okay, this is the first example. Let me take an example for lambda, but we can take the road as a ring. Okay, this one. Look, here we have a uniform charged ring. When I say uniform, we talked about this before, it means lambda is constant. Okay, it's important. In this case, we can take a small portion, as you see here, small dq from the road, and dq equals to lambda dl. dl is a small portion here. Okay, this one, dl. In general, okay, here is dl from here to here. It's road, okay, without thickness. It's very small as thickness. I want to calculate the total electric potential created by this ring at the point P. P is located on the axis of this ring, as you see. The ring has a radius A. And okay, first of all, what we do here, I take a small portion dq with a length dl. Second, I draw the distance between dq and the point P. You know the distance here equals to x squared plus equal to radical x squared plus A square. Okay, to calculate V, you know the relation dV created by dQ. So dQ will create here dV. Here it's not like the electric potential, it's the electric field. We don't have X and Y. It's a scalar quantity. So it's easy to calculate dV. Just you put dV and you calculate its value. dV equals to K dq divided by the distance between dq and the point P. We have x square plus a square. Okay, I need to calculate V, so we do the integral. Integral dV equals to V, we can say V as a point P, equals K is constant. In this case, X is constant, A is constant, so we can get out this one. How can we know if X is constant? We have to move dq on the ring. If X change or not, or A is not changing if we move dq on the ring. By moving dq, A will be constant and X must be constant. And also this one must be constant. For example, if we put here dq, you get this one equals to x square plus a square. Okay, you put like this. Here we have a right angle and here we have a right angle. Okay, you get the same value. Here we have a, here we have x, and this one equals to radical x square plus a square. So we get the same value. So the distance between dq and the point P will not change. And x also, if you change dq, x will be constant. So here we can write x square plus a square, and inside we have dq. So here I don't need to write dq equals to lambda dl. You can put it directly, the integral of dq equals to q. We can write here equals k divided by radical x square plus a square times q. And here we can say q equals to lambda L. L is the total length of the ring. Okay, if you want, you can say here, you know, in this case, if we have a small L equals to R times theta. So L equals to R times theta. If L is the total ring, so the angle theta equals to 2 pi. So in this case, L equals to R times 2 pi. Okay, all the circle. We can write here Q equals to L times R times 2 pi. Okay, so V equals to K divided by x square plus a square, and Q equals to lambda times L. L equals to 2 pi times R. Okay, so we have L 2 pi R lambda. Okay, this is the electric potential created by this ring. Okay, it's easy. Okay, this is about the electric potential. We can do some application later. Thank you.